What are tensors? Yeah, so rotation tensors are tensors. That's right. What else? What are tensors? They're linear transformations that act on what? Vectors to produce vectors, right? So, for example, the rotation tensor is a tensor because it acts on a vector to rotate it, to produce another vector. Now, a rotation tensor preserves the length of the vector it rotates. Okay, so we said that rigid body motion can be decomposed, general plane or general rigid body motion can be decomposed into a rotation and a translation, right? So if I have a rigid body, my origin rigid body motion can be written as a rotation plus a translation. So Q is the rotation tensor and small q is the rotation. Big Q is the rotation tensor and small q is the translation vector. So if I have 2 points on a rigid body, I can write that XA is equal to Q XA plus Q, and XP is equal to Q XP plus Q, right? So if A and B are 2 material points on the same rigid body. So, question, are these Q rotation tensors and this translation vector, are they supposed to be the same for A and B? Why, yes.
Points are fixed on the body.
Right, and also all the points of the body rotate in the same fashion because the body is rigid. So there's no relative rotation between points on the same rigid body, or there's no relative translation between the points on the rigid body, on the same rigid body. So yes, indeed, one rigid body has one rotation tensor, one translation vector, which is a function of time only and not a function of the specific material point or the specific location on the rigid body. So I can say that XP minus XA is equal to Q XP minus XA. And I can take the derivative of this expression to get that VB minus VA is equal to Q dot. Q is a function of T. I can take its derivative. I'll get Q dot XB minus XA. Now this XB minus XA I can write it as XB minus XA is Q inverse XB minus XA. And since Q can be shown to be a proper orthogonal tensor, Q inverse is equal to Q transpose. So VB minus VA is Q dot Q transpose xb minus xa. What does a proper orthogonal tensor mean? A proper orthogonal tensor has the inverse equal to the transpose. So if the transpose is equal to the inverse, what is Q transpose? It's the identity, right? So it's like having matrices and multiplying a matrix by its inverse is the identity matrix. So I can take the derivative of this expression, Q dot Q transpose plus Q dot transpose is equal to I. Sorry, the derivative of I is 0. Any questions so far? Questions? So I'm going through in a little bit of detail what we concluded with on Thursday, last Thursday. Okay, so the derivative of the identity tensor, because the identity tensor is constant, its derivative is going to be 0. So I have now that Q dot Q transpose is equal to minus Q dot transpose, which happens to be Q dot Q transpose. Can anyone remind us what is the transpose of the product of two matrices? What is it? You flip them, right? It's B transpose, A transpose. So by this you can check that Q dot Q transpose is indeed Q transpose, which is Q, and then Q dot transpose. So if a matrix and its transpose are opposite, what does this say about the matrix? If a matrix and its transpose are the same, what does this say about the matrix? Then it's symmetric. And if a matrix and its transpose are opposite, what does this say about the matrix? So if A is equal to A transpose, then A is symmetric. If A is equal to minus A transpose, we're assuming A is a square matrix here. If A is equal to minus A transpose, then what kind of matrix is A? Any guesses? A is Q symmetric, right? So a symmetric matrix looks like this. A, B, C, D, E, F, and then these elements repeat. Or maybe I'll do it like this. A11, A12, A13, A12 and A21 are going to be the same. So these are going to be the same. So that's a symmetric matrix. How many independent components does a symmetric matrix have? 6, right? Any questions? Questions so far? Okay. Whereas this Q-symmetric matrix, and you can double check that this matrix is equal to its transpose. Whereas for this Q-symmetric matrix, the diagonal terms are going to be 0, A12, A13, A23, So this is a skew-symmetric matrix. You can double check that its transpose is its opposite. How many independent scalar components does this skew-symmetric matrix have? 3, like a vector. So then there's an equivalence between multiplication by a skew-symmetric tensor or skew-symmetric matrix and a vector cross product. So we can define an equivalent vector so that these two operations are the same. Omega here is called the angular velocity vector. Okay? So the angular velocity vector is such that these two expressions are the same. Multiplication by q dot q transpose is the same as crossing omega cross any vector. The angular velocity is a property of the rigid body. So each rigid body has an angular velocity that is a function of time and not a function of location on the rigid body, or not a function of the material point on the rigid body. Okay? Let's look at a small side note here. If I have a rigid body, this, and it rotates into this, okay, so this line became this line. What's the angle between the two lines? I'll call it theta. This is going to be the same angle between any two corresponding lines in the reference configuration and in the current configuration. So this is here my reference configuration, and this is my current configuration. So if I follow this line, it's rotated to, oops, I didn't draw this well. Let me draw it again in a smaller scale. Okay. So I have this line in the reference configuration and this line in the current configuration. The angle between the two is called theta. Okay? Now if I take another material line in the reference configuration and look at the same line in the current configuration, what do you think this angle is going to be? It's going to be the same. It's also going to be theta. And it's going to be the same for any other material line of the rigid body. So if I think of this line and this line, also theta. We can show this from geometry that when a rigid body is rotating, the angle between any two material lines, between any pair of material lines, one of which is in the reference configuration and the other one is the corresponding line in the current configuration, the angle between them is going to be the same for all material lines on the rigid body. So the rotation angle, and this is a very simple 2D depiction, but the rotation angle is a property of the rigid body. It's not a property of each individual material line having a different rotation angle. And the same for the angular velocity of the body. The angular velocity of the body is a property of the rigid body. Does that make sense? Yeah? Now, we can take the derivative of this expression to find that AB minus AA is equal the derivative of omega is alpha. We're going to call it the angular acceleration. Plus omega cross xp minus xa. The derivative is going to be vb minus va, which is omega cross xp minus xa. So here alpha is equal to omega dot is the angular acceleration. One more thing before we start with exercises, one more note is that for any corotational vector on the rigid body, so say for example I have a corotational basis on the rigid body. So I have a rigid body and I have a corotational basis. How do I find the derivative of the corotational basis? Well, I can still use this equation. Because the corotational basis is a vector, for example, the Ex vector is a vector between two material points on the rigid body. Do we remember what the corotational basis is? What was a corotational basis? Okay, but what's like the more rudimentary definition of the corotational basis? Yes. Exactly, a basis that is fixed to the rigid body that rotates with it. And in the case of plane motion, then we define it as the way you mentioned. So Ex is a corotational vector that is fixed to the rigid body. So we can take Ex, we can look at it as a vector between two material points on the same rigid body, right? So I can calculate Ex dot by this equation here. So Ex dot would be equal to omega cross Ex. And that's true for any corotational vector on the rigid body. So then in summary, if I have two material points on the same rigid body, I can relate their velocities, I can relate their accelerations, and if I have a corotational basis on the rigid body, I can calculate its derivative as such. Okay? Let's look at an example. Last week I gave you set 15. And I think we did problem 4. Let us look at problem 1. Set 15, problem 1. Okay. Okay. So the device shown rotates about the fixed z-axis with an angular velocity omega is 20 radians per second. So that's the angular speed. What is the angular velocity then? Which is a vector if the angular speed is 20 radians per second and it's depicted in the figure here, what is the angular velocity, omega, of the device shown? It's 20, but it's a vector, right? So what is the direction of the angular velocity? I'm rotating about which axis? Easy, right? And that's going to be the case for most of the problems we're going to do in this class. We're going to do planar rotations of rigid bodies, so that the axis of rotation, we're always going to take it to be along the fixed EZ axis. So 20 EZ radians per second. Okay, what about the angular acceleration? Here it says that it's 40 radians per second squared. So what's the angular acceleration vector equal to? Negative 40. Why the negative? Because EZ is pointing up and alpha is rotating in the opposite direction. Any questions so far? Omega is rotating this way, pointing along positive EZ. Alpha is rotating the opposite way, pointing along negative EZ. Okay. We need to determine the instantaneous velocity and acceleration of point B. So we need to determine VB and AB. What do we do? Take a minute, think about it, chat with your neighbor, and then let's come up with a strategy to determine VB and AB. Okay, so any ideas? What do we think? How are we going to determine VB? So what's the equation then? VB is equal to omega cross RB. Okay, where does this equation come from? This one, right? You're going to relate the angular, the velocity of two material points on the same rigid body, which are O and B. So VB minus VO is equal to omega of the rigid body that's given cross XB minus XO. What is VO here? 0. Why? It's along the axis of rotation, it's fixed, it's not moving. So VO is 0. VB is what we want to calculate. Omega is the 20 EZ. Now what is XB minus XO? So this vector from B to O. Yeah, I could go from O to A, then from A to B, right? So that would be, what is the distance from O to A? OA along my corotational EY, right? So that's XB minus XA. Sorry, XA minus XO. And what about XB minus XA? What is that equal to? Right. So xp minus xa, it has two components. What are the directions of these two components? Minus? What did you say? Sorry, I didn't hear you. Right, exactly. AB and then a positive y, positive z component. AB cosine 60 EY plus sine 60 EZ. Okay? Now, always during this motion, small ez is equal to big Ez because that's the fixed axis of rotation in this motion. Also, at the particular instant considered, it seems that we're taking the fixed basis and the rotational basis to coincide. Okay, so since we are considering only one instant in time, it is okay not to take a rotational basis. We can take the fixed basis to coincide with the rotational basis at this instant. But usually, if I'm looking at how a rigid body moves in time, then I put a rotational basis on the rigid body, which is not going to be the same as the fixed basis, right? Here, because I'm looking only at one instant in time, then it's convenient to take the rotational basis and the fixed basis to be the same at this instant. What is Ez cross EY? Ez cross EY is equal to Ex. Raise your hand if you agree with this. Ez cross EY. Is it negative or is it positive? Raise your hand for negative. Raise your hand for positive. Take a second, discuss. Okay, so what is it going to be, positive or negative? Negative. Negative Ex plus 20 AB bar. Okay, that's the same. Minus cosine 60 Ex plus, what is Ez cross Ez? 0. Right. So that's our answer. The B is purely going to be along rotational Ex. Do we see that the velocity of, does it make sense that the velocity of B is purely horizontal along rotational Ex? Yes. The Ez cross Ez component, they cancel out. Yeah. Sorry. No worries. Any other questions? Okay, take 2 minutes and solve for the acceleration of point B with your neighbor quickly. And then we move on to another problem. Take a minute, solve for the acceleration of point B, and the final answer is there. So if you don't get there in 2 minutes, let me know. Yes, for example here, if you want to find VA and you want to go this route, you cannot say VC minus VA is whatever, because they don't belong to the same rigid body. You have to find VB, then do VBA minus VB, for example.
Thank you.
You're welcome. Any questions? The next problem we're looking at is problem 5. Raise your hand if you're done with finding AB. Raise your hand if you need a little bit more time. Okay, cool. Any questions? Anyone? Okay, let's hop on to problem 5. When you have time, if you haven't finished problem 1, finish it. Let me know if you have questions. Let's hop to problem 5. The elements of a simplified clamshell bucket for a dredge are shown. A cable which opens and closes the bucket passes through the block at O. With O as a fixed point, determine the angular velocity omega of the bucket jaws when theta is equal to 45 degrees. It don't have to be theta is 45 degrees. We're going to do it for any angle theta as they are closing. The upward velocity of the control cable is 0.5 meters per second as it passes through the block. Okay, how many rigid bodies do I have here? 4. What are they? The 2 bars, OA, OB, and then the 2 claws. Okay? So then, how many separate rigid bodies? 4, and each of these rigid bodies is going to have a different angular velocity, right? Now, because of symmetries, they're going to be related. So, for example, the angular velocity of OA and the angular velocity of AB, what can you say about these two? Yeah, they're going to be equal and opposite. So, if one rotates this way by a certain angular speed, the other one is going to rotate the other way by the opposite direction, same angular speed, because of symmetries. You can think about it this way. Okay. So think about it this way. I have a horizontal, fixed horizontal line. I can think of this angle and this angle that these two that OA and OB make use the same horizontal line. So if this angle, I call it theta OA, the angular velocity of bar OA is going to be theta dot OA. Easy. This angle, I'm going to call it theta OB. The angular velocity of bar OB is theta dot OB easy. Can I relate theta OA and theta OB? These two lengths are equal. So what kind of triangle is OAB? It's isosceles. So these two angles, the base angles are equal. So this is equal to theta OA, right? So theta OA plus theta OB is equal to what? Pi. Theta OB plus theta OA is equal to pi. Do we see that? So what is the relationship between theta dot OA and theta dot OB? They're opposite. Theta dot OB is equal to minus theta dot OA. How did I obtain this result? By taking the derivative of this equation. So because of the symmetries of this problem, the angular velocity, for example, of OA and OB are equal and opposite. Equal speed, opposite direction. Any questions? Okay. Make sure your neighbor doesn't have any questions. If they do, let me know what those are. So chat with your neighbor. Do they have any questions? Questions? Yes. Yes. So in this class, we're only considering planar motion, planar rotation. So we're always going to take our axis of rotation to be along EZ. So here, rotation is happening in this plane, and EZ is going to be outside the page. And a rotation like this would be positive EZ, and a rotation like this will be negative EZ. Okay? Yes. So you can think of this as a fixed point. This part is rotating about this axis. Yeah. Does this answer your question? Cool. Any other questions? Questions? Does anyone's neighbor have any unresolved questions? Okay. So what is happening? The cord is being pulled up. The jaws are going to close. We need to determine the angular velocity of each jaw, the angular velocity of the bucket jaws. Okay. What do you think we should do? Take a minute, think again. What do we think we should do? We need a strategy to determine the angular velocity of the jaws. And we can just look at one side, and because of symmetry, the other side will have the same speed but opposite direction, okay? So we can just look at one jaw, and we'll deduce what the other jaw angular velocity is. So we need the angular velocity of this rigid body, right? Which equation contains the angular velocity of this rigid body? Yeah, but between which two material points on the same rigid body? A and C, right? Yeah, so VA minus VC is equal to omega AC cross RA minus RC, right? Okay, write that equation. Is it a chalk?
It's a good shot. I don't want to use that.
Can you open it?
Yeah, okay. It's the famous Japanese brand. Yeah. I'll remember.
Oh, no, I've tried that chalk.
You don't like it?
It doesn't erase well. Can you give me one? I'll try.
You want the colored one?
No, the white one. Yeah, it doesn't erase great, you'll see.
But the wax, the next event can be choppy translational.
Oh, yeah. Okay. Okay, so what do we think? So we want to find the angular velocity of the jar, right? So what equation contains the angular velocity of this jar here? The angular velocity of this rigid body. There's only one equation that contains that angular velocity. Right, but between which 2 points on this rigid body? A and C, right? So VC minus VA is equal to omega of the AC. So what's omega AC? It's the angular velocity of the rigid body containing both A and C cross XC minus XA. So then in this equation, what is known, what is unknown? Do we know VC? Yes. What is it equal to? VC is equal to 0.5 EY. Okay, do we know anything about VA? No. So that's one vector unknown in the plane, two scalar unknowns. So that's two unknowns. What about omega AC? Do I know anything about omega AC? I know something about it. Its magnitude is unknown, but do I know something else about omega AC? Thank you. Its direction. What is the direction of omega AC? It's along EZ. Could be positive or negative. What about XC minus XA? I could find that from geometry, right? We can determine from geometry, not necessarily easy, but we can do it. So this is one vector equation in the plane. How many scalar equations is that? Two scalar equations. How many scalar unknowns? 3, right? 2 in VA, 1 in omega AC. So again, how many scalar equations? 2. How many scalar unknowns? 3. So not enough equations. What is the other? What is another equation we can add to this? What is it? Law of sines of what for? We're going to use that to find XC minus XA from geometry. I don't quite get it. How would you use the law of sines to find VA? Any other ideas, any other equations we can use? Exactly, VA minus VO. So that's another equation for a different rigid body, the body OA. VA minus VO. What is VO equal to? 0, because it's a fixed point, is equal to omega. Now, that's omega of a different rigid body, omega OA, cross XA minus XO. So VA is the same, two unknowns. Omega OA is one unknown. So then in total, I have 4 scalar unknowns, 4 scalar equations. I can solve this. So maybe I'll call 1, 2, 4 scalar equations and 4 scalar unknowns. Solvable. Okay? So then I need to do the nitty-gritty details. I need to actually determine XA minus XO and XC minus XA, and we're going to use the sine rule and the cosine rule. Okay. So now we're going to have to go to geometry to find XA minus XO and XC minus XA. So for this, I need your help. What do you think we should do? O, C, O, A, C, this is 90 degrees, and this is theta over 2. How can I find, and I'm given LOA, and I'm given LAC. How can I determine XA minus XO and XC minus XO? Take your time, think about it. Take a minute, think about it, and then let me know what to do. Any ideas?
I'm assuming symmetry. So here's 500.
Any ideas? We're going to use the sine rule, the cosine rule, I think. Any ideas? What do we think? Ideas. Anyone? Anything? Yes.
We know that theta is 45, so
Okay.
you can say that the angle of C is 180 minus 90 minus theta.
Right. Okay. So theta over 2 plus 90 plus this angle should be 180. So this is okay. So theta over 2, call it beta. Theta over 2 plus pi by 2 plus beta is equal to pi. So beta is equal to pi minus pi by 2 minus theta over 2. So that's pi by 2 minus theta over 2. Okay. Great. Then what? Yes.
You can use the law of sines and use length of OA, and then the angle that you have to find is theta O with the length of AC.
To find this angle, right? So call this angle gamma. Sine gamma over LAC is equal to sine beta, which is sine pi by 2 minus theta over 2, over LOA. So I can find gamma. Gamma is equal to sine inverse, a bunch of terms. And now that I know gamma, how can I write XA minus XO? If I know gamma, how can I write XA minus XO? It's gonna be equal to what? Sine gamma minus EX, cosine gamma minus EY, right? So this vector is gonna have negative EX and negative EY components. Any questions? And then XA, well, I can determine XC. No, wait. I can find XC minus XA. XC minus XA is this vector, which is equal to LAC positive EX, so cosine beta, and then EY, sine beta EX minus cosine beta EY. Is that correct? And then you can, did I make a mistake? Is that correct? Right, any questions? Then you can take the cross products and find the answers. Solve the system of equations for unknowns, get the answers. Right, and here you're gonna need your projections. You're gonna have to project the scalar equations. You can project them in an elegant way and solve for the unknowns one after the other without solving a system of equations, yes?
For XC minus XA, can you explain how you got the signs for your EX and EY component?
Yes. xc minus xa is this vector. Positive ex, negative ey. The ex component is is sine beta, and the ey component is cosine beta. Okay. Any other questions? So please complete this problem. You have to practice your projections, and that's why it's super important here to be careful with our notation, right? If we didn't put vectors, if we didn't align vectors in the above equations, then instead of saying that we have two scalar equations, we'll think that we have one scalar equation. It's going to be a complete mess. It's basically a demonstration. If we don't underline vectors, it shows that we don't understand what's going on. Okay. Any questions? Let us consider, so our new topic right now is instantaneous center of rotation. Okay. If I come back to this problem, VC is pointing up, right? How is the angular velocity of OA? Is it going to be along EZ? Is it going to be along EZ or along minus EZ? VC is pointing up. This is rotating like this, right? Omega AC. What about omega OB? I think omega OB, if omega AC is like this, let's look at the figure again. If omega AC is like this, it's closing. Then omega OA might be this way. Okay. What is the velocity of point A? What is the direction of VA? We have an equation for VA, right? VA, okay, VA minus VO is omega OA cross XA minus XO, right? VO is 0. So then VA is equal to omega OA cross XA minus XO. What does this say about the direction of VA? If VA is equal to the cross product of two vectors, what does this say about the direction of VA? It is what? Exactly. VA is perpendicular to both of these vectors. So VA is perpendicular to both XA minus XO, which is this one. So VA is perpendicular to this vector. And it's perpendicular to EZ, omega OA, which is along EZ, which is perpendicular to the plane. So VA is in this plane, and it's perpendicular to omega, and it's perpendicular to XA minus XO. So what is the direction of VA? Can you show me with your fingers? Yeah. So it's perpendicular to this line. It could be either pointing up or down. Because omega OA is like this, it needs to be pointing up. So this is VA. It's perpendicular to omega OA. Okay? Is it possible to have VC pointing up and VA pointing inwards? Is it possible to have this? VC pointing up and then VA pointing inwards? Is that a possibility? Yes. What about in this configuration? Let me ask you the question this way. If I have a bar, two ends of the bar, they have two different velocities, right? Oops. So I have A and B. VA, is it possible to have VA to be like this and VB to be like that? And the bar is rigid, remember. So is that possible? Take a minute, chat with your neighbor. What do you think? Yes, no, and then why? What do we think? Aren't perpendicular to what? Why would they be? If it's rotating and one point is fixed, then you have a perpendicularity. But here, no need. Okay, so who says this is possible? Raise your hand for yes. Raise your hand for no. Why is this not possible? Why no?
Because there's a parallel component of velocity that oppose each other.
Right, so that would mean that the body is stretching, right? Which is not possible because this is a rigid body. So what your friend is saying is, I have this rigid body. If I take the projections of these velocities along the rigid body here, this says that VA has this component along the rigid body and VB has this component along the rigid body. This is only possible if the rigid body is stretching, right? Which by definition a rigid body cannot do. So this is not a possible motion, which if we go back to here, this also says that this is not a possible motion. When we have a rigid body, the components of the velocities of the endpoints, or any 2 points along their connecting line, needs to be equal. So I'll need that VA dotted with this direction U to be equal to VB dotted with this direction U. So VA dotted with U, VB dotted with U, they need to be equal for the body to be rigid, right? It was a question in a midterm last fall here, which asked students to show that for 2 points on the rigid body, show that VB minus VA dotted with XB minus XA is equal to 0. How would you show that? How would you show this for a rigid body? If A and B are 2 material points on the same rigid body. Yes.
Can you do it where you turn it into VB minus VA is omega cross XB minus XA?
Right.
And then if those terms dotted together.
Okay, if I start with VB minus VA is omega cross XB minus XA, then what? Yes. No worries. So it's a great start. If VB minus VA is equal to omega cross XB minus XA, then what does this say about the direction of VB minus VA relative to XB minus XA? Yes, so what is the relationship between VB minus VA and the XB minus XA in terms of directions? They're perpendicular, right? So VB minus VA is omega cross XB minus XA. By the definition of the cross product, VB minus VA is perpendicular to both omega and XB minus XA. So then these two vectors are perpendicular, their dot product is 0. So I can draw XB minus XA is this vector. This vector dotted with the difference of the other two vectors should be 0. So the difference between these two vectors should be perpendicular to XB minus XA. Okay. That was a small detour. Going back to this figure, this bar OA is rotating about the fixed point O, right? This bar OA is rotating about the fixed point O. If I wanted to find the velocity of a point that's midway between O and A, what would its direction be? Same as VA, which is perpendicular to the bar. Why? Again, the question is, I have OA that is rotating about the fixed point O. We already established that VA is perpendicular to OA. Why again are VA and OA perpendicular? Right. VA is omega OA cross XA minus XO. VO is 0. So VA is perpendicular to XA minus XO and omega OA, so it's like this. By the same reasoning, the velocity of this point here is perpendicular to this line. Okay? And the velocity is going to be proportional to the distance from the origin. So the velocity of the point is proportional to the distance from the origin. So if I wanted to draw the velocity profile of this line, the velocities of the points would be like this. So if I go back to this question here, if I have fixed point rotation, I want to draw the velocity profile of this line. I have, for example, points A, B. I can say that VB minus VA, I will erase this bit here. Okay, here. VB minus VA, VB minus VO is omega cross XB minus XO. VO is 0. So VB is perpendicular to omega cross XB minus XO. I can even take a rotational basis, EX, EY. I can say that omega EZ crossed with DEX it's gonna be omega dy. So that's VB. VA, same thing. So this point B has velocity VB perpendicular to OB. This point A has velocity VA perpendicular to OA. What is the relationship between the magnitudes of VA and VB? VB is twice VA because B is twice the distance from the origin O. So for example, if I had a point at 3/4 the distance from O, its magnitude would be the average between VA and VB. So my velocity profile would look like this. It's linear. Why? Because of this equation. Does that make sense? Questions, 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 questions? Does that make sense? Okay. So O is the center of rotation, and then we have these nice properties. Because the center of rotation is fixed, we have these nice properties that the velocities of all the points are perpendicular. So the velocities of all the points on the bar are perpendicular to the distance between O and that point. Now, when we have rigid bodies rotating in the plane, not all rigid bodies are rotating about a fixed point. For example, is the bucket in the problem we just solved, problem 5, is it rotating about a fixed point? No, it's not rotating about a fixed point, right? OA is rotating about the fixed point O, but the bucket AC, so the rigid body containing the points AC is not rotating about a fixed point. But what we can do is we can say that AC is rotating instantaneously about a point that we call the IC, or the instantaneous center of rotation. The IC, or the instantaneous center of rotation. So AC at this instant is rotating about some point, but the location of that point is gonna change. How do we define the IC? It's a point that acts like a material point on the rigid body, and its velocity is instantaneously zero. It's zero at this instant. So what is the IC? Oops. So the IC acts as if it's a material point on the rigid body, but it doesn't have to be a material point on the rigid body. You can think of it as belonging to a massless extension of the rigid body. Okay. So if I had a random rigid body rotating about a fixed point, if I have point A on the rigid body, I know that VA is going to be perpendicular to OA, right? If I had point B on the rigid body, I know that VB is going to be perpendicular to OB. Now, if I have a rigid body that's not necessarily rotating about a fixed point, but I have the velocities of two material points on this rigid body, VA, VB, I can say that the instantaneous center of rotation should satisfy that VA minus VIC, because it acts like a material point on the rigid body, it should satisfy that VA minus VIC is omega cross XA minus XIC. And VB minus VIC is omega cross XB minus XIC. The instantaneous center of rotation should have zero velocity, so I'll get rid of the IC. So VA needs to be perpendicular to XA minus XIC. So again, the instantaneous center of velocity has zero velocity. So VA, this IC is equal to 0. So VA is perpendicular to XA minus XIC. VB is perpendicular to XB minus XIC. So the IC needs to belong to a perpendicular line to VB passing by B. So the IC belongs somewhere here on this line and somewhere here on this line. So the IC is here. So at this instant, you can think of this body or look at it as it's rotating above this IC here, the instantaneous center of rotation here. So this body, at this instant, it's rotating about this instantaneous center of rotation. But this point is not fixed. At a different instant, the location of the instantaneous center of rotation can move. Does that kind of make sense? So if I go back to this bucket problem, I have VC pointing up, VA pointing perpendicular to OA. About which point is this jaw rotating at this instant? In other words, what is the instantaneous center of rotation of the jaw at this instant? What do I do? Draw the lines. Which lines? Perpendicular to VC passing by C, so this line. And the other line that is perpendicular to VA passing by A, which is the extension of OA, right? So this is the IC of this jaw bucket at this instant. It's located here. So you can look at the jaw at this instant as rotating about this point. Does that make sense? And if I want to find the velocity of any, or the direction of the velocity of any other point at this instant, all I need to do is, for example, I want to find the velocity of this point. I'll take the line from the IC to this point, and the velocity of this point is going to be perpendicular to the IC. And the closer I am to the IC, my velocity speed is going to be less. And the farther away I am from the IC, then my speed is going to be greater. Does that make sense? Okay. To make sure you understand, what I want you to do is to look at problem 6 in the same set. Look, problem 6, how many rigid bodies are there in problem 6? 3. CB, BA, and AO. I want you to draw the velocity profile of each of these rigid bodies at this instant and locate the instantaneous center of rotation of each of these rigid bodies at this instant also. So problem 6, it's a 4-bar linkage. I want you to find the IC and the velocity profile of each rigid body at the instant depicted. Okay, so let us see. Where is the instantaneous center of rotation of bar BC? The instantaneous center of rotation of bar BC at C, right? It's already rotating about a fixed point. The instantaneous center of rotation is just the center of rotation, which is C. What about OA? O, right? What about AB? So how would you draw the instantaneous center of rotation of AB? Yeah? What do I do? Can you walk me step by step through this? Velocity of B perpendicular to BC, so like this? Okay, VB. VA is perpendicular to VO. Yeah, extend BC and OA, depending on the angles. the instantaneous center of rotation of BA is along the intersection lines of OA and BC, right? The IC of BA is along the intersections of OA and BC, which I think with the configuration depicted here, it's going to be somewhere down here. Does that make sense? The instantaneous center of rotation? Okay. So the instantaneous center of rotation has 0 velocity at this instant, but it can move in space. So it's acceleration. Oops. Okay, I need someone who's tall to come and help pull this